All right, so to start this new unit, we're basically just going to take everything we've already covered and convert it all into a rotational perspective. Okay, so let's start talking with rotational motion. Now, one of the things that we've already kind of done with rotational motion was talking about circular motion. Okay, so let's just recap some of the things we can get from a circular motion. So the first was a time, right? We could calculate a time that it takes to go completely around the circle. We called that the period. If we wanted to know how many times we've completed a lap around a circle within a certain amount of time, we would call that the frequency. So let's think of an object that's moving in a circle of some given radius. We know that it has a tangent velocity. Okay, it moves off in a straight line, tangent to the circle. Okay, and we could calculate the period by simply taking the distance the object travels divided by the speed at which it's moving at. And so the distance of a circle is the circumference, 2 pi times the radius, divided by the tangential speed. Okay, again, all of this should be review. The frequency then is simply the inverse of the period. Okay, and then recall the units. The units for period are in seconds because we're talking about a time. And the unit for frequency is 1/seconds, which we call hertz. And you'll see that shorthanded with a capital H and a lowercase z. Okay, and then one of the other things we defined was the centripetal acceleration, okay, which remember was the tangent velocity squared divided by the radius. Okay, so these were all of our circular motion quantities, but they weren't quite talking about the rotation of the actual object, and so that's what we're going to do now. We want to break it into all of those individual measurements to describe a rotating body. So to do that first, we're going to start with position. So let's define an angular position. Okay, so let's imagine an object moving in a circle. So we're just going to make like a small segment of a circle here in the corner. Okay, now that circle has a radius r to it, and we have an object of some mass, and that object is going to move through to some new point. Now when we're taking these measurements of a circle, okay, it should make sense that we're measuring through an angle. Okay, this angle is what we define as the angular position. Now, we're used to measuring angles in degrees, and for more mathematical reasons than anything, when we make these angular position measurements, we don't use degrees, we're going to use radians. Okay, radians are in fact the standard unit. Okay, as we move around this circle, this curve that we've created on the outer edge of the circle has another term to it we call the arc length. Basically, that means if you were to cut that segment of the circle and lay it out to a ruler, then you could get a linear measurement for how far you've moved around the circle. Okay, and so to calculate the arc length, which we typically you'll see in like a math textbook designated with the letter S, we simply take the radius that we're located at from the center of the circle times the angle that we move through. Okay. Now, as we're doing some of these problems, one of the more common unit you're going to see is known as the revolutions that a circle makes. Okay, and a revolution is simply a 2 pi radian. So the question then, which one do you prefer? And as I mentioned a little earlier, radians are the standard unit. Therefore, all of your calculations should be done in radians. Okay, so there's going to be a lot of conversion to go from revolutions to radians and then sometimes back to revolutions. What's important is that you cannot do any calculations unless your numbers are in radians. Okay, so let's consider the next quantity. So again, we're going to look at a circular segment. So we have a mass and it's moving around a circle of radius r, and it moves to some other angle. Okay, and the point is that we look at this in terms of what's the rate at which this movement occurred. So we traveled through an angle and we did that in some amount of time. Okay, this is what we define as an angular velocity. Okay, and we simply take the change in angular position divided by the change in time. Okay, now you'll recall that this is pretty much how we found a regular velocity, by looking at the change in position over time. Okay, and so it's pretty analogous to what we're doing here. Now, the only other thing we need to do here is we need a variable to define angular velocity. Can't use v because v represents linear velocity. So what you'll see in the textbook is actually a lowercase omega, and it's important that this is not a w. Okay, we're not trying to define work and we're not trying to define weight. We're just trying to look for something different. So in the book, it's lowercase omega. When you draw it out, you just need to know what it is you're making. So you can draw it as you would a w all you want, but just know the variable name is not a w, it's omega. And so angular velocity is the change in angular position over time. Now, being that this is a calculus-based physics class, that also means we can look for an instantaneous angular velocity, okay, which of course would be found in the same way we did with an instantaneous linear velocity. You would simply take the limit of our time interval to go to 0, because again, instantaneous means a very, very, very tiny amount of time. And by definition, this is a derivative. Okay, so let's look at our conversion for the arc length then, because this gets us an interesting idea in terms of how to convert between linear and rotational. So consider arc length again. Arc length s was the radius times our angular position. Well, if I want to take, or say I take a derivative of both sides. Okay, so we've got two quantities here. Now, the first thing we want to look at is on the right side. Notice that between the two variables, r and theta, r does not change. We are located at the same radius at every instant we're moving around this circle. So if the radius is constant, I can simply pull it out. Okay, and then as we go through it, so on the left side, the derivative of a linear distance over time is what we define the velocity. Then we have the radius times the derivative of angular position over time, which we have defined as the angular velocity. So this represents a way that we can convert between a rotational and angular quantity. And notice it looks very identical to the arc length formula, okay, just in different quantities, right? In the arc length, we're finding a distance or a length, so we do a radius times the angular distance or length. And to find a linear velocity, we do a radius times the angular velocity. Okay, so this gives us an idea of some ways we can convert between rotational and linear quantities. Okay, if we want to find a linear distance, we simply multiply r to the angular distance. And if we want to find linear velocity, we do radius times angular velocity. And of course, we could go the other way too, right? We could divide the radius to both sides, and then we can convert a linear to rotational. Okay, but these are representing our stepping points to how do we convert between linear and rotational stuff. Okay, and then one other thing to notice is that in our velocity equation, this is really the tangent velocity. So again, considering the circular segment, and this object is moving from 2 points, okay, then it moves through an angle in some time, and that's what defines the angular velocity. Now here's something important to understand. No matter where you are in terms of radius, right, you could be close to the center, that first line segment where theta is labeled, or you could be a little bit further out, or you can be even further out. Each one of those is the same angular displacement, right? You've gone through the same angle. that means you would have the same angular velocity at any one of these points. The difference here is that each segment has a different tangent velocity. In fact, the further out you get, the greater that tangent velocity becomes. And think about why. You're rotating through the same angle in the same amount of time at every different radii. That means the further out you go, the more distance you have to cover in that same amount of time. So you should be moving faster. Okay, and that's important. The angular speed is the same throughout. The linear speed is going to be different. The further you are from center, the greater the linear speed you will have. All right, now we mentioned that in circular motion, one of the things we had with acceleration was the centripetal acceleration, right? An acceleration that points towards the center of the circle. Well, so recall centripetal acceleration is the tangent velocity squared over the distance or over the radius. Okay, now what if we didn't know the tangent velocity? What if we knew the rotational speed, the angular velocity? So we can calculate and do some manipulations to get the tangent v and then plug it in and we're done. Or if you think about the substitution, that radius times angular speed is the tangent velocity. We could do a little algebra, and what we end up finding out is that the centripetal acceleration can be found directly by doing the square of the angular speed divided by the radius. Now, this is not a formula that's on your formula sheet, nor is it something you necessarily have to memorize, but you do have to memorize how to do the conversions, the radius times the respected quantity. Okay, and that extends even further to the next thing, which is your angular acceleration. Okay, so we're going to define angular acceleration using the same steps and doing the same thing we did to develop regular acceleration. Right? Regular acceleration was the change in velocity over time. So it stands that the angular acceleration should be a change in angular velocity over time. Okay, and the variable that you'll see for this, it's actually a lowercase alpha symbol, which for all purposes looks like a sketch of a fish. Okay, so the acceleration, angular acceleration then, if we want to know the instantaneous, same thing, it'd be the derivative of angular velocity. Okay, so if we go back to our conversion, that tangent velocity is radius times angular velocity, we'll see that you're going to get the same conversion for acceleration, right? To get the tangent acceleration, you would take a derivative of the velocity, which means take a derivative of the whole right side of that conversion. Again, the r is constant, so we're only looking at the derivative of angular velocity, which, as we've already defined, is your angular acceleration. So it turns out that the tangent acceleration is simply the radius times the angular acceleration. So again, in comparison with everything, if we do radius times angular velocity, we get linear velocity. If we do radius times angular position, we get linear position. Okay, now I wrote an x here instead of an s because, again, s is arbitrary, but for physics, we're talking along a line which we've defined as either x or y. Okay, so these three represent our three ways to convert from rotational to angular, or divide over the r, from linear to angular. Okay, and that's going to be a pretty powerful step in terms of how we develop all of the physics we've done since August into rotational perspectives. Okay, so if we think back, the first thing we did was kinematics. Okay, so let's start there. Now, a simple kinematic equation, you'll recall, was the velocity is equal to the acceleration times the time plus the initial velocity. Now, let's say we want to convert this into rotational form, because instead of an object moving along a line, we have, say, a disk that's rotating at a certain speed with a certain acceleration. Okay, now, how do we apply kinematics to rotational objects? Well, we simply start by making all of our necessary substitutions. Okay, so we're going to convert this to rotational, which means velocity To get linear velocity, we do radius times angular velocity. To get acceleration, we do radius times angular acceleration. And time is just time. There's no rotational or linear form of time. It's just time. And then the initial velocity would simply be the radius times the initial angular velocity. Okay, now if we do another algebra step here, we'll see that everything has an r attached to it, which again, remember we said was constant. Then I simply divide off the r, and what we're left with is the angular velocity is equal to the angular acceleration times time plus the initial angular velocity. Right, now notice, look at the two kinematic equations. The first one, the one that we're used to, is a linear kinematic equation. And this new one is the exact same thing with the rotational variables. So to a degree, there's no new equations anywhere in this idea of rotational kinematics. Okay, they're all the same equations, just simply write in the rotational forms. Okay, if I make a table of linear to rotational quantities, we can write out every single kinematic equation in rotational form. Okay, now I'm skipping the step of make the full substitution of r times the angular quantity, but simply because it's going to be the same result. The r is going to cancel away. All right, so notice each equation is the exact same form and the exact same mathematical operations as the linear form, but just replace it with rotational quantities. Okay, now there's a few things that I also want to add to this, okay, and just a few kind of warnings, if you will. Okay, the first is that, remember, angular position should be measured in radians. Angular speed should be measured in radians per second. And angular acceleration should be in radians per second squared. These are the units that are necessary to do calculations. Okay, again, a common other form of this is revolutions. So, for example, we knew angular position could be in revolutions, and a common one for angular velocity is what we refer to as RPM, which you've probably heard of. You see this in like a car panel, for example, because it's referring to the number of rotations that occur in your engine, right? This is revolutions per minute. Okay, so that's important. It's in revolutions per minute. That's the common one you're going to see, but you can't do calculations with that. You have to convert that into radians per second before you can do any math. Okay, there's only one other part to this that I want to make sure you're aware of. Okay, and that is sign convention. Okay, because when we're talking about linear motion, we knew that positive and negative mean something, right? Positive means you're going to the positive side of 0, and negative means you're going the other way. So how do we do signs, rather the directions, in rotational? Okay, and the idea is simple. When we're making angles, right, think of a standard XY coordinate grid. Whenever you make an angle, you always measure it in a counterclockwise rotation. It's always measured from the positive x-axis, right? If you remember your quadrant labels, they go quadrant 1, quadrant 2, then 3, and then 4. And notice they're going in a counterclockwise direction. So in fact, we consider counterclockwise, okay, so notice the abbreviations, counterclockwise as the positive direction and clockwise as the negative direction. So if we're doing these problems and one of them happens to say that it's rotating counterclockwise, you know that means positive. And if it says it's rotating clockwise, that means negative. Okay, so those are our signs and directions. Okay, so the final thing we're going to do is we're just going to do a quick example. Now, so this example came out of number 42 from your textbook. Okay, and this is in chapter 4. Okay, we're actually in chapter 12, but chapter 4 is where the introduction of this rotational quantities began, so that's where we're going to start. So I highly recommend you go back and read through those last few sections of chapter 4 before you get into the chapter 12. So here we have a problem. It says a bicycle wheel is rotating at 50 RPM. When the cyclist begins to pedal harder, giving the wheel a constant angular acceleration of 0.5 radians per second squared. What is the wheel's angular velocity in RPM 10 seconds later? And then part B, how many revolutions does the wheel make during this time? Okay, so we're doing a kinematics problem, but in rotational form. So how do we solve kinematics in the past? You start by listing all of your variables. Okay, so you'll notice then that this is the same rotation, or sorry, the same list that we did with linear form. 2 angular positions, 2 angular velocities, angular acceleration, and time. And then we go through and we list what we know. So typically for the angular positions, you might as well say we started at 0. There's no harm in saying we started with no angular position. Now the final angular position we don't know, but that's actually the question in part B. The initial angular speed is 50 RPM. Okay, now again, pay attention to the units. We're going to have to do something with that. We can't do calculations in revolutions per minute. The final angular speed, we don't know. That's the question in part A. The angular acceleration was 0.5 radians per second squared. And then time was 10 seconds. Okay, so if we're going to solve for the final angular speed, we again go to our kinematic equations and we pick the one that fits. Okay, but before we do that, we got to get rid of the RPM. We've got to convert that into radians per second. All right, so I use the bridge method like you guys did in chemistry, and you saw me do this earlier in the year with unit conversions. So I start by saying that it's 50 revolutions on top over minutes, because there's your revolutions per minute. And we convert 1 unit at a time. So I'm going to start by converting revolutions. So in order to cancel that, I need to write 1 revolution on the bottom. And 1 revolution, remember, was equivalent to 2 pi radians. Okay, now that mathematically gets rid of our revolutions minute, or unit. Now we have to get rid of minutes. So it started on the bottom, which means now I have to write minutes on the top, where 1 minute is 60 seconds. And then that mathematically gets rid of minutes. So now you just crunch it out. 50 times 2 pi divided by 60, and you will get 5.2 radians per second. So that is the angular velocity we use in our calculations. Okay, so to start the problem out, we're going to pick a kinematic equation that's working for our variable list. So the easiest one would be angular velocity is equal to angular acceleration times time plus the initial angular velocity. And we plug in our numbers. Okay, easy enough. And then we calculate this out. You're going to get 10.2 radians per second. Okay, and that's the answer. However, if you look back in part A, it tells us very specifically that it wants the answer in RPM. So we've got to go through and do the conversion process again. Okay, now it's slightly different because we started with RPM and went to radians per second. Now we want to reverse that process. So we start out by writing it as 10.2 radians over seconds. So if I convert the radians first, 2 pi radians gives us our 1 revolution. Okay, and that gets rid of radians. And then seconds, we convert 60 seconds is 1 minute. So that gives us a total of 97.4 RPM. And that would be our answer for RPMs. Okay, now let's go to part B. So now, how many revolutions does a wheel make during this time? Well, now we've got every variable filled in except the one we want. But remember, it's good rule of thumb. If you can avoid using a calculated answer, like 97.4, or the 10.2 rather, if you can solve it before using that calculated answer, do that first. So ignoring the fact that we just found final angular speed, the only equation that would work is the longer one. So angular position is 1/2 the angular acceleration times time squared plus the initial angular speed times time plus the initial angular position. Okay, so now we go through and plug in our numbers. So that's 1/2 of 0.5. The time was 10 seconds. Don't forget to square that. The initial angular speed, remember, radians per second, was 5.2. Again, time was 10 seconds, and we started with no angular rotation. Sorry, no angular displacement. So we crunch all this out, and you get a nice and even 77 radians. Okay, and again, that is our answer. However, looking at part B in the question, it wants to know it in revolutions. So we're going to take this number and convert it to revolutions. Okay, so again, 2 pi radians is 1 revolution. And when we crunch this out, we get 12.3 revolutions. Now, one thing to be careful about. While this conversion is correct to 12.3 revolutions, pay attention again to what the question's asking. How many revolutions? By definition, a revolution is a complete circle. So when you look at this answer, how many complete circles did you cover? It's not 12.3 because 0.3 is not complete circle. So when you're doing revolutions, you always truncate off the decimal. Okay, how many revolutions did you complete? You completed 12 revolutions.